Okay, so if you've been following along in the textbook, you noticed that we skipped a bit. And the bit we skipped is the following. It's the theorems. So a theorem of logic is a conclusion that you can prove using no premises. So there's a whole bunch of things that you can prove in our logical system, starting from nothing. Starting from thin air, you can prove these theorems. And given what we've got so far, I mean, it should be well, it will become fairly clear. I'll show you at least one or two proofs of this stuff, how that's possible. At the end of chapter 2 in the Parsons textbook, there's a list of 125 theorems. And potentially, every single one of those theorems is a rule that we could introduce. So in the original system that the Parsons textbook is based on, they allow you to cite theorems as rules in your proofs. But that takes us from, I don't know, what have we got so far? We've got 6 that we introduced last time. We started with 4 or 5, so we've got maybe 10 rules in our system. We could potentially add 125 extra rules, and by the time we're done this course, there'll be a whole bunch more theorems we'll be able to prove, which makes our system very, very complicated indeed. So I propose not to do that. So we're not going to include theorems as rules that you can cite in our system, really in the interest of keeping it compact. We want to make the system that you're supposed to learn as simple as possible, with as few rules as possible, with still a lot of the same sort of derivational power that you would have otherwise. I hope you agree, 125 rules is way too many rules to expect you to learn. So, with that in mind, we're not going to learn almost all of these. But I am going to introduce to you today 5 rules, I think it's 5, which are going to be called derived rules. So everything we've learned so far are what are called basic rules. These are rules that basically you can't derive without introducing them as kind of primitive operations. The rules we're going to learn today are based on theorems, and they're just really helpful rules. They're really helpful for getting through derivations in an efficient way. And that's why we're introducing them. They're powerful, they're fairly simple, there's a fairly short number of them. So these are the derived rules. They're going to help get you through derivations in a much faster way than otherwise you would have been able to. So that's what we're going to do today. Today I'm going to introduce to you these 5 derived rules. Negation of conditional, conditional's disjunction, separation of cases, De Morgan's, negation of biconditional. So we're just going to go through these kind of one at a time and describe them, and then we'll do some examples using them. None of the derivations that you have for this week involve these derived rules necessarily. You have to unlock them to be able to use them on Logic 2010. So unless you've done that, you can't use these derived rules yet. But I'll include some of them as exercises for next week, and I'll give you the solutions to the derivations so you can use them going forward. Okay? Any questions? Sorry, but I usually start out by asking if there's any questions about course business or anything like that. Before we dive in, are there any kind of course business questions? Or questions based on the very notion of derived rules? No? Okay. Okay, so let's talk about these rules. First one, negation of conditional. So if you have the negation of square then circle, then you can get square and not circle in one move. You're allowed to do this. And of course, vice versa. If you have square and not circle, you can get, it's not the case that if square then circle. Okay. So I'll show you the proof for this in a little bit, just to kind of get us warmed up again with derivations. But you can convince yourself that this is a valid rule of inference just by looking at the truth table for the conditional. So recall that this is the truth table for the conditional. And there's only one line on which the conditional comes out as false. The following 2 things have to be the case for the conditional to be false. The antecedent is true, and the consequent is false. Any other situation, the conditional comes out as true. Okay, so if the negation of a conditional is true, that means that the conditional must have been false, meaning those 2 things must be the case. True antecedent, false consequent. So look again at this rule. If the negation of that conditional on the left-hand side is true, it must be the case that the antecedent, square, was true, and the consequent, circle, was false. Yeah? You can see that just based on the truth table for the conditional. If you know it's false, then you know that situation obtains. And of course, you can do the same thing in reverse. The second rule is just the same thing in reverse. If you know that square is true and circle is false, then you know that the conditional, if square then circle itself, is going to be false, and therefore the negation is going to be true. Reasonably convinced that that's a good rule? Yeah? Well, so how do I know that it's true? I must have, if I have it as input, that means I must have it as a premise, or I have derived it on an available line. Yeah? So these rules take something as input, and that input has to come from somewhere. You're not allowed to just make up inputs. And the only two places that you can get inputs are either from premises or from available lines. Available lines are things that you've shown follow in a truth-preserving way from your premises. So that's how we know the first thing is true. Okay. Would you like to see the derivation for this proof? For this rule? Okay, let's do that. I'm not going to do derivations for all of them. Some of them are long and, I mean, this is going to be long-ish, but negation of biconditional is a really long one, so I'm not going to do that one. But I think this is the first theorem I've tried to prove with you. Is that right? Okay, so it's a theorem. This is a thing that I'm going to try to show. I'm going to try to show this, it's not the case, if it's not the case, that if P then Q, biconditional, P, no, that's not a P, P and not Q. Okay, and do you see how this is the same as the rule that I just showed you? So so the biconditional says two things. It says if I have this negated conditional, not if P then Q, then I can get P and not Q. So that was one half of the rule. And the other half of that biconditional just says you can go in the opposite direction as well, right? So this theorem, if this theorem is true, then that rule is a good rule. Do we accept that? Okay. Nobody's protesting, so I take it you accept. Okay. All right. So this thing is a biconditional. When we're trying to show a biconditional, what we do is try to show one half of the conditional, and then show the other half of the conditional, and then put those two conditionals together using conditional to biconditional. If you recall, we're going to do this thing and then this thing. Yeah? Okay, so that's the plan. We're going to show first, if not P then Q, then P and not Q, and then we'll try to do the other half. All right. That means that we get to assume if P then Q for conditional derivation. And now we're going to try to show on that basis P and not Q. Okay. We can go ahead and do very soon, this will be a useful thing. So in derived rules, we'll have a derived rule later today that makes this into something useful. I'll just do it out of habit right now. Okay. Now, it's a theorem. So, okay, I've set up my show lines. Now it's time for me to survey my resources. It's looking kind of grim, isn't it? Because I have no premises to work with. This is a theorem. There's no premises. What have I got available? Well, I've got 3. And I've got the not super helpful looking 5. All right. So I'm feeling a bit stuck already. Immediately, right off the bat, I'm feeling a bit stuck. So I propose to write myself a show line. recall that thing that I said we might want to do is to use, so if I have, I mean, once I've proved negation of conditional, this thing will be useful to me. Right now it's useless though, except potentially as a contradiction generator, right? As a way of generating a contradiction. So if I can get the opposite of not if p then q, then I can close this subderivation off as an indirect derivation. So I want to show, on that basis, I'm going to write an unprompted show line for if p then q. Okay, so I'm writing this show line because I think maybe I'll be able to show the contradiction of line 3, and then this half will be good. So assume p for conditional derivation. I'm going to show q, and we got not q, assume ID. All right. Okay. Now, I can't show if p then q directly. I haven't got the materials for that. What I have now got the materials for, however, is to generate a contradiction with something else. What I've got the materials for is the stuff to generate a contradiction with line 5 now. Because I've got p, so 7 repeat, and line 9, I'm going to adjoin them. So now I've got p and not q. And that's useful because it contradicts this thing, line 5. Line 5 is not if it's not the case that p and not q. This is p and not q. So if I say line 5 repeat, line 10 ID, I can close off this show line. So I'm still trying to generate a contradiction with line 3. But I did it by generating a contradiction with line 5. Okay? Line 8, I therefore did a conditional derivation. Notice how useful it was for me to write this second show line, this show line on line 8. This is the one that I told you is optional. You don't necessarily need to write the show line after you started a conditional derivation, but this time it was really helpful because it gave me not q, and not q is what I used to generate a contradiction with line 5. Okay, I'm going a little faster now. I hope that's okay. When you're writing the tests, you're gonna have to go fairly fast. I'm gonna ramp up the speed as we go along. Okay, so on line 6, I've shown if p then q. Why was I trying to do that? Oh yeah, I was trying to generate a contradiction with line 3. So what I've done here, I can say 3 repeat 6 ID, and now I've shown this thing. Again, notice that I didn't prove, well, I proved p and not q, not by getting something that contradicts directly p and not q. What I contradicted was something else that I already had. Okay, so now I've done my conditional derivation. So 14, on line 4, I did a conditional derivation showing 1/2 of the conditional. Okay. So now I'm going to try to show the other half of the conditional. So, show, and just to remind you, this is the plan, right? Here is our plan. So far I've done this thing. Now I need to do the other thing. Okay. Line 15, I'm going to try to show the other direction of the conditional. So, if p and not q, then it's not the case that, it's not the case that if p, then q. Okay. I hope you don't mind me moving this thing up. I mean, I've just run out of space. But also, everything above this is boxed off, so I'm not allowed to use it. And also, there's no premises, so that I don't have to remember what my premises were. Okay. So, I'm going to assume P and not Q. I can assume that for conditional derivation. And I'm going to try to show not if P then Q. Once again, that second show line is pretty useful to me because now I'm allowed to assume ID on it. You can't just assume ID at any point. You can only assume ID directly after a show line. So writing that second show line allowed me to get if P then Q. And this half of the conditional, the biconditional, is going to be easier to show. So look, I'm just going to pull down 16 repeat, bring it into my subderivation, P and not Q. I'm going to say line 19, simplify, and then I'll simplify off the P. Line 18, modus ponens, giving me Q. Of course, on line 19, simplify, I've got not Q. And hooray, I've done it, right? 20, 21, ID. Line 23. So on line 17, we did the conditional derivation, a bit faster that time. It didn't take as many lines. Box and cancel. Okay. So now, reviewing where we were, we did the other half. Yeah? So we set out trying to show this biconditional, and we showed one half on line 2. We showed the other half on line 15. So now we can say, we can put them together, 2, 15, and we're starting from conditionals and going to biconditionals, CB. We've shown, if it's not the case, that if P then Q, biconditional, P and not Q. 24, direct derivation. Okay, so that's a fairly long proof. Now that was showing both directions of the theorem, right? So if you were, suppose you're in a basic rules derivation. Sometimes we'll allow you to use these derived rules. Sometimes we'll require that you don't. But if you're like, look, I have this negated conditional. I have not P then Q. If only I had if P then not, if only I had P and not Q, that would be really helpful. Well, you can always just do this derivation. You can always do these set of moves and get the thing that you wanted. It's nicer if you have the derived rules because then you can do it in one line. So if I was allowed to use the derived rules, this proof would be much, much shorter. Any questions about this proof? Yeah?
Can you just scroll back down?
Yes, yes. I'm sorry this is very long. Yeah. Yeah. Other questions? Okay. Let me show you this proof with, if we were allowed. So imagine instead of trying to prove this rule, imagine we just had the rule negation of conditional. Let me show you what that would look like. Oh. So, da-da-da. All right. So we still need to, if P then Q, we're going to assume this for conditional derivation. We're going to try to show P and not Q. But now it's really easy. Now we say on line 3, repeat, negation of conditional. And that gives you P and not Q. And you are done. 5, direct derivation. That means on line 2, we did a conditional derivation. Yeah? Much shorter, much nicer. I want to show P and not Q, then not P and Q. Assume this for conditional derivation. Show not P and Q. Well, 9, repeat, negation of conditional gives me, sorry, this should be a conditional, not an and. I'm whipping through this because these are now officially trivial. P, then Q. Well, 9, repeat, negation of conditional gives us, it's not the case that if P, then Q. So 11, direct derivation. And 12, conditional derivation. Look, now it all fits on one screen. Right. So the same getting from A to B gets much, much shorter when you're allowed to use the derived rules. Of course, if you're trying to prove that the derived rule works, using the derived rule is kind of a, it wouldn't make sense, but okay. But you see that it makes things much nicer for you. And just a note, when you're writing these out, if you've got a negated conditional, NC is the rule to get to the conjunction. If you've got the conjunction, NC is still the rule to get to the negated conditional. So it's the same rule, can take you in either direction. Yeah? Questions? Okay. Then let us move on. Okay, negation of conditional. I don't think we've got time to show you all of the proofs for all of these, but I just wanted to show you at least one, I don't know, to get us re-warmed up about derivations. Okay, so that was negation of conditional. Here's another one. Conditional as disjunction, CDJ. Another quite useful rule. So if you have a conditional, so this one's got 4 forms based on where the negation is, but look at the top left-hand side for right now. If you have a conditional, you can get, it's not the case that square or circle. So let's think about that for 1 second. And again, probably the best way to understand why this rule works is just to look at the truth table for the conditional. Think what has to be the case to make it true that that conditional is true. So again, just focusing on the top left hand, you have this conditional. Well, that means that it's either true that the antecedent is false or the consequent is true. Okay, let's look again at the truth table. So the conditional is true. We know the conditional is true. We've been given that as input to the rule. Now, what can we conclude on that basis? Either the antecedent is false, in which case it comes out as true. So if the antecedent is false, that's the 2 bottom lines. So if the antecedent is false, the conditional is true. Or the consequent is true. So if the consequent is true, in either case where the consequent is true, the conditional is true. So if you know the conditional is true, you know one of these 2 things, or both, must be the case. Either the antecedent is false, or the consequent is true. Yeah? Yeah?
For me, I think this looks like MTP, that if we leave that one-sided disjunctions, we'll get the other here.
That's right. So MTP is the rule that you would use to maybe understand this. So you can understand this by thinking about how you would use, so again, let's just, I think if you take the time to understand just one version of this, the others should fall into place. If you think about using MTP on the bottom line of that top left-hand version of this, right? You want to get either one of those out of it. right? So I want to find one of those two disjuncts must be true for that second sentence to be true, right? That's what the disjunction means. At least one of these is true. So if you have it the case that circle is true, then you have it the case that the conditional is true. Or if you have it the case that the antecedent is false, then you have it that the conditional is true. Another swing through this maybe, if this isn't doing it for you, there's a couple of options. You can just kind of take some time with the conditional, the truth table for the conditional. Another way of thinking about this is like really savor how weird the material conditional is. It's a really weird way of representing if-then, okay? It does not match up exactly with what we mean by if-then. Because so take the top sentence, if I'm a reptile, then I smell great. Now, that's true if both the antecedent and the consequent are true. I'm both a reptile, I'm a great smelling reptile. That's one way of making it true. Another way of making that true, given the weird material conditional, is for the antecedent to be false. As a matter of fact, I am a mammal, I am not a reptile. Therefore, if I am the subject of that conditional, it's true. The conditional is true. If I'm a reptile, then I smell great, regardless of how I'm smelling today, right? Because anytime the antecedent is false, the whole conditional comes out as true. It's just not what we mean by if-then in normal language, but that's what the material conditional says, okay? So that makes the sentence, if I'm a reptile, then I smell great, logically equivalent to either I'm not a reptile or I smell great, okay? Again, there's a kind of built-in counterintuitiveness here. So if you're feeling that this is counterintuitive, it's extremely likely that what you're feeling is how weird the material conditional is. So again, your options are spend some time with the truth table for the material conditional, or your other option is simply memorize these as rules. Like if you beat your head against this long enough and it's just not working, you can kind of just memorize these as rules. The other thing that you can do is to look at the proof, which you'll be forced to do, don't worry. You'll look at the proof of the theorem that corresponds to this rule. So I'm going to make you do that, so that's another way of, another cut through this to understand this rule. But, okay. So I don't think we have time to do, I would like to do a couple of examples of derived rules proofs, so I don't have time, unfortunately, to go through the proofs for all of these. So if there are no further questions, I'm proposed to just move on to the next one. Yeah? Okay. Right, and just a note on what you can use this to do quickly before. It's very useful if you want to show a disjunction, this is potentially useful. So if you've written a show line for a disjunction, then what you can do is write a show line for if not P then Q. So if you want to show P or Q, you can write a show line for if not P then Q, and then start a conditional derivation. And then once you're done that conditional derivation, once you've canceled off that show line, you can just use CDJ to get the disjunction. So this is a move that you can make potentially to show something in a derivation. Okay. Okay, here's another one. Separation of cases. I'm going to go ahead and confess that I very rarely use this in derivations. Of these rules, it's my least favorite. But hopefully, my personal feelings are irrelevant here. Hopefully this is you can understand why this should be the case. So Here's a natural language version. I'm going to come back to this slide in just one second, but here's a natural language version of this. So if you know that one of two things is true, and you know that either of those two things leads to a conclusion, then you get the conclusion. If you know that A or B is true, and you know that A leads to C and B leads to C, then you know that C is true. So here's that. So counterintuitively, these two cases are the exact same thing that I just described. So square or circle. Suppose you know that, you have that on an available line. Furthermore, you have that square, if square is true, then triangle is true. And you have, if circle is true, then triangle is true. So the first line gives you that one or the other of these, or both, has to be true. And then the second two lines give you that either of them would be good enough to get you to the conclusion triangle. Well, then you get triangle. Right? So here's an argument. Look, I'm either staying in tonight and watching Netflix, or I'm going out with my friends. If I stay in tonight and watch Netflix, I'm going to have a good time. If I go with my friends, I'm going to have a good time. So I'm going to have a good time. It's a good argument, right? If you have the truth of those premises, that's a deductively valid argument. Okay. Now, why is that the same as this other thing on the right? This other thing on the right looks very different. Notice that the thing on the left has 3 inputs, by the way. It's the first rule that we've had with 3 inputs. So you need to cite 3 lines to get this rule to work. The thing on the right only cites 2 lines. But it's got the or statement kind of built in. Because in our system, you know, if something is not true, then it's false. If it's not false, then it's true. Yeah? So you know either square, so as a matter of logic, you know that either square is true or square is false. That means either square is true or not square is true. One of those has got to be true. Right? So that's sort of like providing the top line in a built-in sort of way. So if you've got the case, look, if it's raining, then I'm going to be happy. If it's not raining, then I'm going to be happy. So I'm going to be happy. Love these arguments where I get to be happy. That's a good conclusion. Okay. Okay. Any questions about this? Okay. Again, people differ in their derivation styles. So there's lots of different ways, lots of different go-to moves that you can get accustomed to. This could become your go-to move. So I don't want to discourage you from thinking about separation of cases, but I can tell you that I literally never use this rule. So if this is boggling your mind, you can get through all the derivations for the rest of this course without using this rule. Technically, you can get through all the derivations of this course without using any of these derived rules, because you can always just make the moves in the basic rules. They're just sometimes much, much longer. This one, it cuts out some, but not very much. Anyway, so separation of cases. All right. Here's one that you're going to use a lot. This one you should learn pretty well. Okay, in natural language, this says, the negation of a disjunction is equivalent to the conjunction of the negation of its parts. And of course, conversely, the negation of a conjunction is equivalent to the disjunction of the negation of its parts. Ugh. All right, don't worry about that. Here's a kind of procedure for doing De Morgan. So this is something you can do to disjunctions, conjunctions. So if you have a disjunction that's negated, or a conjunction that's negated, here's what you can do. You knock off the negation, you flip the disjunction to a conjunction, or a conjunction to a disjunction, and then you negate both of the parts. Okay, let me show you the rule, and then I'll come back to this procedure, and this will hopefully make sense. So, De Morgan's has 8 versions, but let's focus on these top 2 first, and then you'll be able to see how the procedure I just gave you applies to them all. So, starting with, I got a conjunction. I got an and statement with a negation out front. Okay? So you knock off that big negation out front, you flip the and to or, and negate both of the parts. Yeah? So it's like you distribute the negation to the parts, and then flip the and to an or. And it's exact same if you've got a negated or statement. You knock the negation off the front, flip the or to an and distribute the negation to both of the parts. Yeah? And the bottom two rules are just the same thing in reverse. Just you can go either direction. The other direction is less commonly useful. The one that you'll probably use a lot are the top two. Those top two are the ones that are the most useful versions of De Morgan's. They're the ones you're going to want to remember. I mean, do try to remember them all, but those are the really important ones. There's a versions that you can do unnegated. So if you have an and statement, you can get the negated opposite. Those are less commonly useful. Okay. And just natural language version of this, because I think it's sometimes helpful to ground it in language. Suppose it's true that I am both happy and tired. So we get a true conjunction. That's equivalent to saying I am neither not happy nor not tired. Bad writing, but same idea, yeah? Top one is saying it's true that I'm happy, it's true that I'm tired. Bottom one says, look, it's not true that I'm unhappy or not tired. Did that help at all? Probably not. Okay, let's go back to the procedure, because there's a recipe for this. This is the De Morgan's recipe. So now you've seen the rule. In every version, this is the way the recipe goes. And you can either run this recipe backwards and forwards, but just memorize it in the forwards direction. So you got either a negated disjunction or a negated conjunction with a negation out front in the bracket, outside the brackets. You'd knock off the main negation, you flip the conjunction or disjunction, and then negate the parts. Okay? Okay. So this rule you will very likely use all the time. This is a rule that's super useful because previously, having a negated conjunction or a negated disjunction wasn't a really helpful thing to have. You could use it as a contradiction generator, but you can't get at the parts of that sentence, right? The negation is the major connective of that sentence. You can't use your rules like MTP or simplify to get at the parts of that sentence. Using De Morgan's, now, so on the top left-hand side, you start from something where the major connective is a negation. On the bottom, it's now the major connective is a disjunction, and you can use MTP on that to get one half or the other. If you've got a negated disjunction, you should be thrilled, because now you've got something where the major connective is a conjunction, and you can just simplify those parts, right? You get both halves of that. So if you have it's not the case that square or circle, then you know that it's both false that square and false that circle. Very useful thing to have, whereas previously that wasn't a super useful thing to have. Okay? Okay, De Morgan's. I love this rule. It's my favorite of the 5 derived rules. I don't know why I'm telling you my feelings about these rules. It doesn't really matter. But it is nonetheless very useful rule, and you will need to use it. These are kind of less useful versions, but they're on tap if you want them. Okay. Yeah, so one more natural language version. This sandwich is either rotten or has blue cheese. You got a smelly sandwich. You don't know what it is. Either something's gone bad or it's got some very expensive cheese in it. So you can derive from that. It's logically equivalent to, it's not the case that the sandwich is neither rotten nor does it not have blue cheese. Sorry, this should say, nor does it not have blue cheese. You know one of those two things must be true. All right, I don't know if that helps at all. Okay, one last rule. Negation of biconditional. This is, again, a pretty helpful rule. So if you have, it's not the case, so negated, square, biconditional circle, you can get square, biconditional not circle. And of course, the reverse. Okay. So thinking about what does the biconditional say? The biconditional says that square and circle have the same truth value. They're either both true or they're both false. Okay? Biconditional says these two things are either both true or they're both false. And the biconditional is true in either case. So if square and circle are both false, the biconditional square circle is true. Okay? So if you have a negated biconditional, that tells you precisely the opposite situation is the case. One of those is true and one of them is false. Right? A negated biconditional says these two things have different truth values. If the biconditional says they have the same, a negated biconditional says they have different truth values. Okay. Now that turns something that was previously, again, not that helpful to you. Maybe you could use it as a contradiction generator. But the thing on the bottom there, on the left-hand side, the thing on the bottom, now that's a biconditional, and you can pull out the two conditionals from it. So you can, from that bottom thing there, you can pull out if square, then not circle, and if not circle, then square. So now you can break that into its parts, and the parts are more useful to you than the original negated biconditional. Yeah, yeah.
In the last part where you were saying the biconditional, how you can pull them out,
Yeah.
are you flipping the negation from the circle to the square? Or?
No, it would, so from this you would, so on the left-hand side there, if you said biconditional to conditional, you would get either if square, then not circle, and you can also get if not circle, then square. Yeah. Yeah. Okay, so I can't imagine, well, no, I can imagine the following scenario where you'd need the thing on the right. Suppose that you have on a previous line biconditional square circle. If on a previous line you have the truth of biconditional square circle, then you can use negation of biconditional to get this negation, and then that's your contradiction. So if you're trying to close off a subderivation with ID, then that right-hand side is potentially useful. I'm not going to lie, the one on the left is the one you're going to use way, way more. So these derived rules let you get through a proof in a kind of more mechanical way, where you're really just pulling things apart into their parts and using the parts. The scenario where you're using the thing on the right is where you're doing sort of more fancy structured proofs. But the thing on the left is the one you're much more likely to be using. Yeah. Other questions? Yeah.
I was just wondering for symbolization, do you use that for exclusive or?
Ah, very good, very good. So the question is, the negated, for symbolization, could you use that for exclusive or? And yes, that's exactly right. So the negated biconditional is exactly equivalent in truth values to the exclusive or. Just to note, in any time on the symbolizations, anytime you see or, you assume the inclusive or. Assume the inclusive or. We're not going to spring an exclusive or on you. Or in our symbolizations, or is going to default to meaning inclusive or, which is the or that we've been using the whole time, the or that I've been showing you the truth table for. But if somebody was trying to symbolize exclusive or, negation of biconditional is exactly how you do it. That's right. Yeah. Okay. So we're running out of time. I'd hope to show you some examples of this. We'll do that next week. You don't need the examples yet. Just a note on Logic 2010, if you try to use these rules in Logic 2010, you won't be allowed to. It will say you have to unlock them. So what I'm going to do is the following. I'm going to put a list of these rules and the derivations you have to do to unlock them. Furthermore, I'm going to give you solutions to these derivations because you're going to need these rules going forward, and I don't want anybody getting stuck on these derivations. So I'm going to post the list of the rules, some of which will be part of next week's exercise, and solutions to all of the derivations. Try to do them on your own. It will help you to understand and remember these rules. But if you get stuck, I don't want you to stay stuck. OK, thanks, everyone.